Math 287, Cuesta College. I'm Joe Vasta, and today we are covering section 4.3, Subspaces. So before we get into this example, we should probably look and see what a subspace is. So if you have your definition sheet handy, there's the definition right there. Let S be a non-empty subset of a vector space V over F. So we have a subset, not to be confused with subspace. So a subset is just a part of a set. If S itself is a vector space over F with the same operations of addition and scalar multiplication as used in V, then we say S is a subspace of V. So all a subspace is a vector space inside a vector space. A smaller vector space, well, sometimes it could be the vector space itself, but we'll talk about that. So just think of it as a vector space within a vector space. Now remember, a vector space V has to satisfy 10 axioms. And in this class, we did not require you to walk through all the 10 axioms. So let's see what our next theorem says. It basically is really cool because in our homework they're going to ask if we have a vector space within a vector space. And this theorem is going to save us a lot of time. It says S is a subspace of V, so that's a vector space within V, if and only if S is closed under the operations of addition and scalar multiplication in V. So basically you just have to check the first two axioms. Is it closed under addition? Is it closed under scalar multiplication? And that's what we're going to do in a few of these problems here. So in your homework, they ask questions like this. Express S in set notation and determine whether S is a subspace of V. Okay. So the thing that we want to point out about subspaces, a subspace is a vector space in a vector space. That's all it is. Another thing we want to point out is in the homework, you have some problems like number 7 and number 16 and number 18. These ones are the toughest. So do them last. Okay. So that way you'll get practice with some of the other ones, and then you'll have more hope to do these ones. So those ones are the toughest. Do them last. Okay. Also, the thing that I want to point out is your homework says express S in set notation. When you're doing these problems, because they're already going to be kind of different, I'm going to say you don't have to do that part. What I want you to do in your homework is to determine whether S is a subspace of V. Okay? So, is it a vector space within a vector space? So here's the first problem. The vector space that we're looking at is R2. S, when it doesn't say anything else, it means the usual addition and scalar multiplication. We're not going to do anything funky with these vector spaces. That was section 4.2 where things got a little strange. S is a subset of R2. Okay, so there's a difference between the word subset and subspace. So it's a subset, which means it includes some of the vectors in R2. We're asking, is S a subspace? So what is S? S is the set of vectors of the form x, 0. Now what does that really mean? If you're a picture person, let me go ahead and draw some pictures. So here's R2 right here. Here's X, here's Y. Vectors that would be like this would be like 5, 0. So you'd put the tail at 0, 0 and put the head at 5, 0, so it would look like this. And 6, 0 would be the vector that looks like that. And these vectors are all the vectors. You might have one that points the other way, like this. They're all the vectors that can be placed on the x-axis. So that's what we're looking at. Now, even though I crossed this part out, it's worth noting that if you see something like this in the book, here's the set notation for it. S is the set of all vectors that look like this. X, 0. Now your book's going to use a colon for such that. Okay, so we're used to a line maybe from other math books, but you know, math books will differ on that. Such that X is a real number. Let's also note that this is really, we'll just say, the x-axis. And when we say it's the x-axis, we mean it's all the vectors that can be placed nicely onto the x-axis. All the vectors in R2. So there it is. So this is another way of writing it. So what we want to do is we want to check Axiom 1 and Axiom 2. So Axiom 1 says, is it closed? Is this set S closed under vector addition? So you take two creatures that look like creatures from S. And so maybe one of them will be like A, 0, and another one would be B, 0. If I add those together, do I get a creature that is in S? So let's do that. Let's add them together. I know this is very abstract for some of you. In fact, 4.3 might be the hardest section in Chapter 4 altogether. So let's add them. A plus B, 0 plus 0 is 0. So if I add two creatures in set S, do I get another creature in set S? Is this guy in set S? Yes, he is, because in order to be in set S, your second coordinate has to be 0. So this is in set S. So I'm going to say this is an element of S. If you like, you could just say in. This is in S. So this is, we can say, is an element of S. So Axiom 1 passes. So now let's look at Axiom 2. Axiom 2 says, so Axiom 1 says closed under addition. Axiom 2 is closed under scalar multiplication. So we pick a scalar like R, it could be S or something like that, and we take a creature from set S. So the creature from set S, I'll just go A, 0. When I do the multiplication, do I get a creature that is in set S? Let's see. So this would be R, A, R times 0 is 0. Is this guy in S? And he is, because to be in S, your second coordinate has to be 0. So this guy is in S as well. So A2 passes. So when both of these pass, because we had that theorem that said you just need to check for closure under addition and scalar multiplication, then the answer to this, determine whether S is a subspace of V, we'd say S is a subspace of V. And there it is. So we have it. So all this for a yes or a no. Now here's the deal. If you can find, if I could have found a particular example that would have broken this, where it wouldn't have been closed under one of these, I would have come up with that example hopefully from the beginning. But to prove that something is a subspace, you have to check both of the closures. Is it closed under addition? Is it closed under scalar multiplication? Now we're not going to get into formal proof writing in here. Some of you may know that if you took any two vectors that lie on the x-axis and add them together, drawing a parallelogram, you would end up getting a vector that is on the x-axis. So you may be able to verify Axiom 1 visually. Axiom 2 says if you take a vector on the x-axis and multiply it by a scalar, which just changes the length and or the direction, you end up getting something that is on the x-axis. It's almost like these guys, this set under addition and scalar multiplication, they're trapped on the x-axis. They're closed. It's closed under addition, closed under multiplication. And so that's what we have here. So remember, when you're doing your homework, you don't have to do that part expressing S in set notation. And is there a symbol for subspace? There's no universal symbol for subspace. See, S is a subset of V, which means it's part of V, could be the whole thing. So this is the symbol for subset. But people always ask, is there a symbol for subspace? Wouldn't it be great if there was? Subspace. Well, I've seen some books, so this is not universal, they've used the less than or equal to sign. So it says S is a subspace of V. But this right here is not universal, which means not everybody uses that, whereas this one is. This is set theory. Okay, I think we should do another example. And what are the questions here? The questions are, determine whether S is a subspace. So is it a subspace? There it is. So I've actually put this one into the set notation. So here we have it. V is R2. S is creatures that look like this, x comma 1. Okay, so you kind of go down the same path that we did before. You could just say this. Look at this. Here's Axiom 1. Let's take two creatures that look like this. So your first coordinate could be whatever you want it to be, A, and then the second coordinate absolutely has to be 1. Let's take that and add it with another one like B, comma 1. So look what happens with Axiom 1. You end up getting A plus B, comma 1 plus 1 is 2. Now in order to be in this set, sometimes I'm going to call this set the party circle. In order to be in the party circle, your last coordinate must be 1. Is this new guy here in the party circle? No, it's not. This is not in S. So guess what? Axiom 1 fails. Axiom 1 fails, which means S is not a subspace of V. So from now on, I might just say subspace, not a subspace for my answer. And we're done with this problem. Now, we could have, so we're done with this. We could have looked at this and said, oh, I can think of something that will break Axiom 1. So you could have gone like 2 comma 1 plus 5 comma 1, and this gives me 7 comma 2. So you could have done that and said, oh, guess what? That is not in the party circle. So you can then come to the same conclusion. The Axiom 1 fails. So if you can break it with a particular example, that's good enough. Oh, by the way, some of you were thinking this. Axiom 2 could be broken as well, because if you have a vector like 2, 1, and you multiply it by 7, so this is scalar multiplication, you end up getting 14, 7. In order to be in the party circle, your last coordinate for this example has to be a 1, and it is not here. So this is not in S. So both of the axioms are broken, but really you only need to prove that one of these axioms fails, and then you're done. You don't have to prove both of them fail. So this is A2 fails. We proved that with an example. The other thing that I wanted to take a look at is, what do these vectors look like? And so let's do what we did before. So we're done with this problem. We're just having like math nerd moments here. And some of you really don't like this because it is very theoretical. Okay, what do these guys look like? X, 1, it means if the tail is there, or let's see, if x is 0, we'll have 0, 1. And if x is 1, we'll have 1, 1. And x is 2. So it looks like all these vectors, if you put their tails on the x-axis, at 0, 0, sorry, their heads happen to be on the line y equals 1. Okay, so sometimes people just say, oh, well, this is these vectors, this is really y equals 1, which is a line, which is not a vector, but a lot of times when you work with vectors, you can say, oh yeah, the vectors that lie on y equals 1 when you put the tails on the origin. Now notice who is not in here and who is not in this party circle. So I keep saying party circle, so let me just show you what I mean by this. Here's a Venn diagram. There's vector v. Those are all the vectors in there, like 2, 4, and negative 13, 1/2. Well, then here is set S. Okay? And so, yeah, when we added 2 people in set S, we broke out of the party circle. This is the party circle. Well, here's the deal. This party circle does not contain a very important member of the vectors. It seems like he's an insignificant vector, but he's very important. Now, when you looked at this problem here, this one did contain the very important member, and that member is 0, 0. So in order for your set to be a subspace, it has to contain this vector 0, 0, and ours does not contain 0, 0. Therefore, it is not a subspace. S is not a subspace of V. So I'm throwing lots of information at you. Let me go ahead and show you this theorem that I'm referring to. If a subset S, okay, so it says set there, subset S of a vector space V fails to contain the 0 vector 0, then it cannot form a subspace. See, one of the axioms of vector spaces is you have to have the 0 vector, and if the 0 vector is missing, game over. You don't even have to check the axioms. Now, the converse is not the same. You can't go, oh, it includes the 0 vector, I'm done. Then you still have to check the axioms, because we will see examples where the set contains the 0 vector, but one of the axioms is still broken. So what does this mean about when you do your homework? Well, there's a few problems in your homework where all you have to do, I'm not saying it's half of them, maybe it's a little less than half, is look, hey, is 0, 0 included in this set, the 0 vector of R2, which is 0, 0? Absolutely not, because there's a 1 there. So right away, we didn't even have to write all this. We could just say, not a subspace, 0 is not in there. We'll do a few like that where we can catch them right away. But if it does contain 0, 0, then you've got to verify the axioms, or break one of them if you can. So this section is really weird. So just know that, and it doesn't keep getting more and more theoretical like this. Actually, some of you might enjoy 4.4 better than 4.3. Our next problem. Okay, before we do the next problem, we could say S is the set of all vectors satisfying y equals 1. So that's another way we could have said this. Why do I say that? Because look at problem number 3. Problem number 3, it says the vector space, so they'll always give you the vector space. It's R2. And S is the set of vectors satisfying this line right here. Okay, so what are we to do about that? So it's any, we have R2, so we have ordered pairs. So S is the set of vectors, the set of ordered pairs that satisfy this. What is the very first thing we do in these problems when they say, is S a subspace? You check to see if the zero vector is in S. See if the zero vector is in the party circle. So what does the zero vector look like? The zero vector looks like that. And what happens when we plug the zero vector in there? We end up getting 0 equals 6. That's not good. So what does that mean? That means 0, 0 is not in the party circle. Game over, not a subspace. And you're done. So that's what that theorem says. The theorem says if zero vector is not in the set, game over. If the zero vector is in the set, then let's look at axiom 1 and 2. Okay, so that killed it for that. So in your homework, check to see if the zero vector's in there, and you'll be surprised at how fast you can get through some of the problems just like this one. Okay, let's continue. See if I can find problem 4. Is this one? Oh, let's not continue. Let's bring up one other thing. I'd like to do this. Here's X. Here's Y. I'm going to graph this line here to find the x-intercept, set y equal to 0, the x-intercept 3. To find the y-intercept, set x equal to 0, y is 2. I think last time I made the line in green. So all the vectors, when you put their tails on 0, 0, their heads will be on this line here. Okay. Notice this line. So this is the line 2x plus 3y equals 6. Notice that line does not go through where? Doesn't go through 0. That's what we just verified. In this last example, see this line right here? Y equals 1. It did not go through the origin. This might speed things up if you're given ones where the vector space is R2 and they give you a curve. Look at this first one. I didn't actually make the line. The line is actually the x-axis. And look at that line. It goes through 0. Let's do another one. Problem number 4. Your vector space is R2. We'll change that for the next problem. And the set is xy such that x is greater than or equal to 0, y is greater than or equal to 0. So pause the video and see if you can figure out if S is a subspace of R2. Okay, there's a few ways to go about this. I'm going to actually draw the picture first on this one. What does this picture look like? It's all the vectors that where the x-coordinate is greater than or equal to 0, the y-coordinate is greater than or equal to 0. So you would have the vector maybe 1, 2, and 3, 4, and 1/2 comma pi. You would have all the vectors when you put their tail here their head happens to be where? In quadrant 1. So how can I draw that? I can't draw that with just a line. I'm going to draw that by shading. So it's all the vectors in here when you put their tails at the origin. In fact, it's a little more than quadrant 1 because it's a vector right here, like this vector. You know, it's right in between quadrant 1 and 4, so all those vectors as well, and then same with the vectors right here. So that's what the picture looks like. The other pictures look like lines. Now, the question is, does this picture, the shading and all that, does it include 0, 0? And the answer is, yes, it does. Unfortunately, because if it didn't, we'd be like, oh, we're done, no is the answer, and then run away from the problem. So I'm going to write this out so you know that I checked this. 0, 0 is in the party circle. So what does that mean for yes or no on this problem? It doesn't mean anything. It means we have to proceed with the axioms. So the reason I'm doing it this way is because some of you might want to take a picture approach to some of these problems in R2. Now remember, when you add two vectors that are over here in mostly quadrant 1 here, and you draw a parallelogram, are you going to get another vector that is in that area? And the answer is yes. Axiom 1 is actually going to pass. It's Axiom 2 where we might be able to think of something that can break it. So let me write that down. Axiom 2. So you take a vector. Now I'll be algebraic, though some of you can already see how you can break Axiom 2. I'll take a vector like 1, 2. And then a scalar. So scalars are real numbers unless they specify it differently, and they usually won't. So maybe my scalar can be like -3. So look what I end up getting. I end up getting -3, -6, which actually points into quadrant 3, which means this is not in the party circle. Which means S is not a subspace. It is a subset of V, but it's not a subspace. And there's the answer. Okay, now some of you could have just done this by looking at the algebra of this. You would say, oh, I would have the vector 1, 2, or 1, 1, and multiply that by a negative scalar, and then that's not going to be in the party circle. Okay, so you didn't even have to look at the picture. But if you were looking at the picture, you know, you have the vector 1, 2, which is right here. And then when you multiplied it by -3, you had -3, -6, which is, you know, I mean, I'm not doing a very good job here. And that guy is not in the set. Okay. Now, we're done with this, and you don't have to say this, but watch this. You know, FYI, Axiom 1 passes. We don't have to write a formal proof for that. This is just for your information. Because, you know, you got some non-negative numbers and you add them. You know, you take two creatures like this, you're not going to get anything that's a negative number. Okay? You take like A, B, add it with C, D, and A, B, C, and D are non-negative numbers. You're not going to get a negative number. Okay, so FYI, A1 passes. But it's still no. So that completes this problem. Let's go ahead and do another problem. We're going to change the vector space around a little. Now our vector space is M2. And so let's see what we have here. I'm just trying to... Okay. M2 means 2 by 2 matrices. S is the subset of all 2 by 2 matrices with the following form. So this is what S looks like. Okay? So, you know, I mean, S contains... So let's draw our picture here. It was too big. Oh well. Okay, so here's 2 by 2 matrices, and here's the party circle. So someone who lives in this party circle might look like this. 1, 3, and then right here, this has to be determined. This has to be the sum of those. So 4, and then right here, this has to be 0. So that's one of the many matrices living in set S. Okay. Someone who doesn't live in set S would be like this, like 1, 1, 1, 0, or whatever. Because look, 1 plus 1 is not 1, so he lives outside the party circle. The question is, can we break this with either of the axioms? But before we ask that question, does the 0 vector live in there? So what does the 0 vector look like? It looks like 0, 0, 0, 0. Does he have the properties it takes to live in the party circle? Okay, so this coordinate, this element right here, top left can be anything. Top right can be anything. To be in the party circle, this element, the bottom left, has to be the sum of the first row. And is it? Yes, it is. And then this element here has to be 0. And so, looks like the patriarch of the vectors, he's actually partying it up in the party circle. That's actually bad news because it means we must continue and we have to go through the axioms. Now, at any time, you can pause this video and see if you can come up with an example where Axiom 1 is broken or Axiom 2 is broken. Okay, so here's Axiom 1. Axiom 1 says you take 2 creatures from the party circle. So because I don't know if I can break it, I'm just going to go ahead. So say, here's my first creature. A, B, A plus B, 0. And then I'm going to take another guy, and I better use different letters. C, D, C plus D, 0. Okay, they're both in the party circle. So they're general elements. Let's add them together using matrix addition. So this is A plus C, and this is B plus D. And then down here we have A plus B plus C plus D, and then 0 plus 0 is 0. Okay, so this guy is knocking on the door. Hey guys, let me into the party circle. And they're like, well, let's check to see if you can make it to the party circle. Top left element, top right element can be whatever, so we don't care. But down here, this is like bringing the chips to the party. This has to be the sum of the first row, is it? Yeah, A plus B plus C plus D, that's the sum of those 2 elements. And then the last thing is you have to bring some drinks. And bringing drinks is equivalent to having the 0 there. So we're getting it from this information the way it was described. Yep, there's a 0 there, and that sums the first row. So you are in the party circle, let them in. Axiom 1 passes. Okay, well maybe Axiom 2 is the place where it's going to break, or it might pass as well. So what's Axiom 2 says? It takes a scalar like R and multiply it by, let's just say this first guy here, A, B, A plus B, 0. Okay, so what happens when you multiply through that R? Scalar multiplication, you have RA, RB. This is RA plus B, which is really RA plus RB. And then what's R, which is a real number times 0? It is 0. So this guy's like knocking, hey guys, let me into the party circle. And then they're like, well, let's check. First row can be whatever. Okay, did you bring the chips? This is, they're checking this condition here. Is this element in the bottom left corner the sum of the top row? Yep, RA plus RB. And then did he bring a drink? Yep, there's a 0 there. And so you are in the party circle. Come on in. We've just verified that A2 passes. So you can take any 2 elements of set S, add them together. They're never going to leave the party circle, and you can take any element of S, multiplied by any real number. It's never leaving that party circle. So that would mean that S is a subspace. So there it is. I know some of you are like, well, I have a lucky coin that can tell me the answer yes or no, but I mean the important thing is, can we arrive at these answers and be confident that we got the right answer? Let's go ahead and do a few more problems. So that's the bulk of 4.3. There's something at the end about null space, and we will get to that. So here goes problem number 6. Now we're looking at vector space of 2 by 3 matrices. That R, by the way, means the elements in the matrices are real numbers. S is the subset of all 2 by 3 matrices such that the elements in each row sum to 0. Wow. How are we going to do this problem? Well, look at the last problem. How they just said, hey, S is the subset that looks like this. Well, they didn't do that here. They kind of described it with words. And this is going to be an important skill as we go through chapter 4. So we've got to put an element like that up there with A's and B's. And that's what we're going to do for our first step. So what does S look like? Okay, it's 2 by 3. When you're looking to see if someone is in S, the first element can be whatever you want it to be, whatever real number you want it to be. And the second element right here can be whatever you want it to be. Now this is 2 by 3, so it's going to have 2 rows and 3 columns. This third element, well, it says the elements in each row sum to 0. So you've got all 3 of those have to add to 0. This element has to be minus A minus B. Or negative A minus B. Because you don't have a choice for that. And that way they'll add up to 0. Now I could have put the A there and the B there, and then this one would have to be negative A minus B. Now some people make the mistake and they put an A here and a negative A here and a 0 there. Well, that does not get all the possibilities. This gets all the possibilities of what can happen in your first row. Now your second row, you have a C here, because you could be whatever you want. And then here, when you're checking out the matrix, that could be whatever real number you want as well. But the row, the bottom row has to add up to 0 as well, sum to 0. So this element had better be negative C minus D. Okay, the question is, so this is what they gave us here. The elements in each row sum to 0, and they do. So let's check to see if the 0 vector's in there. What does the 0 vector look like? The 0 vector for this one is just the zeros everywhere. Do each of the rows sum up to 0? And the answer is yes. So the 0 vector is in the party circle. We're a little bummed about that, because if it wasn't, we'd say, okay, no, not a subspace, and we'd be happy. So let's check Axiom 1. If I take 2 creatures like this and add them together, will the new creature be also like this? Let's see. Maybe if you can break it with a specific example, then go ahead and try doing that. So I'm taking that first creature that I had. And then I need to know 4 more letters of the alphabet. Ooh, this is challenging. Let's see. A, B, C, D, E, F, and then of course this one has to be minus E minus F, G, H. This is not the Euler number, by the way, in case you were wondering. So this is minus G minus H. Now, you might be to this point of the problem, and you might actually be able to look ahead and go, oh, it fails, or oh, it passes, in which case you might not have to do as much writing. But what I'm going to do is I'm going to do a lot of writing on this. So what is this? We have A plus E. The next element is going to be B plus F. And the last one is going to be minus A minus B minus E minus F. Now notice that row, if you add up those 3 elements, they sum up to 0. But let's look at this. So this is C plus G, D plus H, and then minus C minus D minus G minus H. You sum up these 3 elements on the bottom row, they sum up to 0. So this guy is in the party circle. That is the condition to get into that party circle, is your rows have to add up to 0. Axiom 2. take a scalar like r and multiply by this guy here that we have up top, minus a minus b minus c minus d. And so what do we end up getting? We end up getting RA, RB, and then this is negative RA minus RB. Look, the top row sums to 0. You can see if you were to add that element and that element and that element, you'd get 0. RC, RD, minus RC minus RD. And looks like the bottom row sums to 0, so this is an element of the party circle, which means S is a subspace. I'm not going to fit it. Oh, that looks great. What's happening here? Because I saw the other piece of paper and I planned that. Okay, so subspace. Okay, so that's how you play this game. We'll play the game a few more times here. Problem number 7. Okay, problem number 7. Your vector space is 2 by 2 matrices, and S is a subset of M2 of symmetric matrices, nice, with trace 4. Okay, the first thing that I want to do is let's just take a look at the 0 vector here, and maybe that's the first thing we should have done in number 6. The 0 vector for M2 is 0, 0, 0, 0. Okay, it has to pass 2 tests to get into the party circle. It has to be symmetric. So remember what a symmetric matrix is. It's a matrix where A equals A transpose. Basically, it doesn't matter what's on the main diagonal for the square matrix, but these guys right here, A1, 2 and A2, 1 have to be the same, and they are. So it's symmetric. Does this matrix here, the 0 matrix or the 0 vector, does it have trace 4? Trace is when you add up the elements along the main diagonal, and the trace of this matrix here happens to be 0. So it might have fulfilled the symmetric property, and it did actually, but it does not have trace 4, so 0 is not in the party circle. So it's sad because it's not in the party circle, but we're happy because S is not a subspace, and we're done with this problem. Okay, so let's just do an FYI. And some of you might skip to the next problem on the video. FYI, what does a matrix like this look like? Like we kind of did with the A's, B's, C's, and D's on the last problem. A matrix like this, it has to be symmetric and trace 4. So symmetric means if I have an element there, I have to have the same element there. Okay, so that's symmetric. And trace 4, well, I could put whatever I want there, but these two things have to add up to 4, so I'm going to have to go minus B plus 4. And then notice, look, if you add those two elements, it adds up to 4. So that is what a general element looks like in this set S. But unfortunately, I mean, you can see this. You cannot zero this out where you would get 0, 0, 0, 0 because, you know, if this one's 0, this one is 4. And that's what ruins it. This would have been a subspace if it said with trace 0. I believe it would have been. You could check that out on your own. But it would have included the 0 vector. And I think closure under addition would happen. Yeah, and closure under scalar multiplication would also happen. Yeah, so if this had said 0 instead, I think the answer would be subspace. Okay, that completes number 7. Let's continue to do more problems here. Number 8. Your vector space happens to be n by n matrices. Okay, so there's the real numbers there, and the elements are real numbers. This S is the set of all n by n non-invertible matrices. So this one right here should probably freak us all out because it says n there instead of like 2 or 3. So the deal is, if you get a problem like this in your homework, it's best to just let n equal some manageable number. And the rationale behind that is if we can't even do the case where n is 2, then what hope do we have to do this problem? So I know that sounds kind of bad, but let's just say n is 2. Let's see if we can do it with this. So we have M2, and S is the set of 2 by 2 non-invertible matrices. Okay. First thing to look at is the 0 vector, which looks like 0, 0, 0, 0. Is this vector non-invertible? Now there's a lot of ways of looking at the word invertible and non-invertible. One way is to look at the determinant, and the determinant of this is 0. Determinant equals 0, which means it is non-invertible, which means this guy is in the party circle. If the determinant was non-zero, I know this is a little confusing because we're saying determinant non-zero, it's invertible. Determinant 0, it's non-invertible. Okay, so determinant is 0, what can we do? We have to run through the axioms. And the big question is, can you break any of these axioms? You might want to pause the video and see if you can. And if not, then you would have to see if we verify both axioms. Okay, so one of the axioms can be broken. Now let me just put up a creature that is a non-invertible matrix. 1, 0, 0, 0. So look, if you do the determinant AD minus BC, that is 0, because it's 1 times 0 minus 0 times 0. Can you add that to another non-invertible creature to get something where you would have a determinant that was like 1 or something else? And the answer is yes. If you go ahead and you go 0, 0, 0, 1, that's also in the party circle. So those guys are both non-invertible. Look what you get here. You get 1, 0, 0, 1. That has a determinant of 1, which means this guy right here is invertible. Okay? Which means then, because the party circle is non-invertible, he gets kicked out. He is not in the party circle. We have just broken Axiom 1, which means S is not a subspace. Would Axiom 2 be able to get broken on this? And I think that Axiom 2 would not be able to get broken. Okay. Email me if I'm wrong on that one. So we've just determined that that is not a subspace, which also means if you're in higher numbers of n, the same thing can happen. You can think of the same thing. So we are actually done with this problem because n equals 2, we ended up getting no. And so for general n, you can come up with the same argument and also say no. Let's go ahead and do a few more problems. Number 9 is going to be one that looks a little tougher because it's going to give us a vector space that we really feel uncomfortable with. Real valued functions defined from -infinity to infinity. So functions that would be in this vector space would be like the sine of x, and y equals sine x, and y equals x squared. But y equals the square root of x is not in there, and neither would the y equals tangent x. It has to be defined everywhere for that. So that's weird that that would be a vector space, but it is. And S happens to be functions in V that are odd. Okay? So what does odd mean? Odd means f of negative x equals negative f of x. Physically, what it means is it's symmetric about the origin. Okay, which really means if you're looking at the graph and you turn it 180 degrees, you're looking at the same graph. Okay. This one is a little tougher, and if you can come up with a counterexample, great, we can be finished with it. If you can't come up with a counterexample, then we have to take two creatures that are odd and see if you can add them together and get another creature that's odd. So I'm going to do this one a little differently than all the other ones. I'm going to say, suppose F, Frank, and Gary are in the party circle. And they're like, wow, this is a great party. Now Henry is going to be when you add F plus G. Okay? So all I'm just saying is I'm kind of grabbing onto this and calling him Henry instead of just saying calling him F plus G, because it's going to be easier to verify if he's in the party circle. So Henry's knocking. Okay, so here's the picture here. Here's vector space V. Here's the party circle. And here's F. And here's G, and they're partying, and they hear a knock on the door. Hey, can I come in? Can I come in? Can I come in? Can I come in? And they're like, well, we better check. Oh, one thing we forgot to check. I'm sorry, before we continue the story. The zero vector is just y equals 0. Is y equals 0 an odd function? Yeah, because you put negative in, I mean, you can call this, let's just call it like m of x is 0. You put negative x in there, you end up getting 0, which equals minus 0. So that should have been the first thing we checked. I'm sorry, I didn't check that. So 0 is in the party circle. Okay, so now we get back to the story, and Henry's all, let me in, let me in, let me in, let me in. And they're like, okay, hold on, we've got to see if we can see if Henry is in the party circle. The way we see if Henry is in the party circle is this sort of hazing exercise. We're going to see if Henry is odd. So Henry, we're going to feed him a negative x, and he's all, oh, yuck, what did you just put in my mouth? And so Henry looks like this. So what it looks like is, this is going to be f of negative x plus g of negative x. And because those guys are odd, you can write this as negative f of x plus a negative g of x, or minus g of x. You can factor the negative out of those. So this is negative, and then this is f of x plus g of x. And what is f of x plus g of x? Isn't f of x plus g of x Henry? So this is minus Henry. So, is Henry an odd creature? Oh yeah, he is. Henry is in the party circle, because we've just verified that Henry is odd. He's all, thanks for letting me in. Axiom 2. So Axiom 1 passes. Axiom 2, let's pick a different person. F and G are in the party circle. We'll just say F is in the party circle. And we're going to go like R times F. And we're going to call that Jonathan. And Jonathan's like going to be R times F of X. Well, is Jonathan an odd function? Let's verify it. And they're like, okay, here goes the hazing exercise. We feed Jonathan a negative X and see what he does. Well, Jonathan looks like this. R times f of x. So this is going to be r times f of negative x. And then f of negative x, because f is in the party circle, it's going to be this. It's going to be negative f of x. And that negative can come out in front of the r. So this is negative r f of x. And then this guy right here, r f of x, is just Jonathan. So negative Jonathan. And look, we have just verified that Jonathan, this function that's gotten by going a scalar times f, is also an odd function. So Jonathan's in there partying it up. And that means that A2 passed. And now I'm doing past tense, whereas I think earlier I was saying passes, so it doesn't really matter. I'm not an English teacher. So both of the axioms pass, which means S is a subspace. And so there it is. So yeah, number 9 is going to be the weirdest one. Okay, and number 10 comes in close behind number 9 with being weird. You got the real valued functions defined on negative infinity to infinity, and then S happens to be functions in that vector space that are non-negative, which, if in terms of graphs, these are functions that fly above the x-axis. So maybe you can pause the video and see if you can break any of the axioms. The first thing you want to do is, let's say f of x is 0. Is 0 greater than or equal to 0? Yes, it is. So that guy right there is in the party circle. It's not going to be that easy, is it? Where we could just say, no, it's not a subspace. Can you break Axiom 1? Or Axiom 2, or are we going to have to just go through them both like we did in the last problem? Pause the video and try it for yourself. Okay, so hopefully what you're thinking about is these vectors might look like this guy right here. Okay, so let's just say here's a vector. F of x equals what? X squared, not to be confused with when I said f of x equals 0, but if f of x equals x squared, is there anything you can do? Like add it to another creature that is non-negative, or multiply it by a scalar that might put this guy below the x-axis? And I think you may be able to do that. I think Axiom 2 we can break. We can take a scalar like -5 and multiply it by x squared. Okay, so here's a scalar. And then this guy is in S. And you end up getting -5x squared, which is kind of dumb. I just wrote -5x squared equals -5x squared, which looks like a parabola. Let me circle this in green. That is skinnier, and it's below the x-axis, which means it is not in the party circle. So the answer to this is S is not a subspace. So if you can break one of those axioms, I mean, first check to see if 0's in there, but if it is, if you can break one of those axioms, it's a lot simpler than when Henry and Jonathan were knocking on the door of the party circle, and oh, that just looks bad to look at. Okay? So number 10 was not a subspace. Let's go ahead and look at a few other things. Next problem. Oh, well, let's not look at the next problem. Let's look at some definitions. V, the vector space V, and the vector space just containing the 0 vector are called the trivial subspaces of V. So V is a subspace of itself, just like it's a subset of itself. And the vector space is not very interesting, but it is still a vector space that all it contains is the 0 vector. That's a vector space. Those are trivial subspaces of V. Our next problem is this right here. Find the null space of A. So that's kind of weird that we have a new word here called the null space. So let's take a look at its definition. Let A be any matrix with real elements. The solution set to the corresponding homogeneous linear system, AX equals 0, is called the null space of A and is denoted null space, all one word, A. So what is this? The null space is it's a new word, but it's something we have been doing in Chapter 2. So let's go ahead and find null space. Okay. So we have Ax equals 0 vector. The null space happens to be the solution to that. That's what the null space is. So the right-hand side vector is B. I'm going to go ahead and write out A augmented, which is really just A, and then we concatenate something to it. Let's get this done here. Okay, there's equals what? Equals 0, 0, 0. So that is all a null space is of any matrix. It's just solving Ax equals 0. And it's going to be very important throughout linear algebra, and it's going to spill into differential equations. So why don't we go ahead and do some row operations? It's been a while. I'm going to multiply the first row by -3 and add it to the second row. So -3, 0, 6, -3, 0. So what do I have here when I do that? I end up getting 1. So the first row stays the same. The second row becomes 0, 1, 1, -3, and 0. The third row, what I'm going to do is I'm going to go row 3 minus row 1 gives me row 3. So this is going to give me 0. So 1 minus 1 is 0. 2 minus 0 is 2. 0 minus a 2 is a 2. -5 minus 1 is -6. And then we have 0. What do you notice about row 2 and row 3? Well, they are multiples of each other. So you could go -2 times row 2 plus row 3 gives you the new row 3. That new row 3 will be zeroed out. So let me go ahead and just write the results of what I just said. We've been doing row operations a lot, so I don't have to show every single step nowadays. There we have it. And we're going to go pick some variables because we have some equations. We have a pivot there and a pivot there. This is in row echelon form. It's actually in reduced row echelon form as well. I'm going to pick some variables. It really doesn't matter what I name them. X, Y, Z, W. Because you're not going to see those variable names in my answer. So let's find a piece of paper and write up the equations. So look at this. Well, actually, before we write the equations, let's talk about this. X is bound, Y is bound, Z is free because there's no pivot there, and W is free. Let's start off with W. W is a parameter, T. Z is going to be S, and then second row gives me Y plus Z minus 3W equals 0. Y, we'll circle these ones, plus S minus 3T equals 0. So what does Y equal? Y equals, looks like it's going to be 3T minus S. So this is stuff we've done in the past, but we'll continue on this one, okay? So our first equation says X minus 2Z plus W equals 0. X minus 2S plus T equals 0. It's really good that that was in reduced row echelon form because it makes even solving infinitely many solutions a lot easier. You don't have to put that thing in there. So what does X equal? X equals 2S minus T. Okay, so we have a 4 tuple, and I am going to be picky on the test this time, where we want to write it with the set notation. So let's go ahead and write out the 4 tuple first. So this is 2s minus t, comma, that's your x, and then we have 3t minus s, comma, s, comma, t. Okay, so normally we've been writing our answers in chapter 2 like this, so now we're going to go a little further, and I'm going to show you that you're pretty much going to do this to all your answers, really. You're going to say the set of that 4 tuple such that s and t are real numbers. And so that is the null space of the original matrix, which is that matrix there. So here's a matrix, there's the null space. Now this null space happens to be a subspace. So I'm just giving you something from a theorem. The subspace of R4. Okay. Now it's not obvious that's a theorem. In fact, let me show you the theorem. It says null space is a subspace of Rn, n being the number of columns. And so look, subspace of R4. So you automatically get a vector space within a vector space when you find the null space. Let's go ahead and do a few more examples. Finding the null space, we probably don't need to do a few more examples. You're probably set to go for your homework, but there's something at the very end I'm going to show you that some people were not doing on the exam. So that after I do a few null spaces, we'll get to that. Here is a matrix 1, 2, 3, 4. With this matrix 1, 2, 3, 4, we are asked to find the null space. So the null space, AX equals 0. We're going to write this as 1, 2, 3, 4, the augmented matrix, and then we're going to put a 0, 0 here. What are my variables? It doesn't matter. Now we didn't point that out in the last one. Remember I told you it didn't matter. I picked X, Y, Z, and W. I could have picked happy face, sad face, neutral face, and a moon or something. Do you see X, Y, Z, W in the answer? Absolutely not. You see the parameters. So on this one, I will pick X and Y, but before I do that, I'll do some row operations. I'll multiply row 1 by -3 and add it to row 2. So row 1 is going to be 1, 2, 0, and row 2 is going to be 0. I don't want to mess this up, but I might end up messing it up. -6 plus 4 is -2. Then we have 0. And then I'm going to scale down row 2, so row 1 is 1, 2, 0, and row 2 is 0, 1, 0. I multiplied this row 2 by a -1/2. Okay, so I've got a system here. Here's X, here's Y. Look at this, look at that bottom equation. Well, one thing you can see is that everything is bound. Here's a pivot, here's a pivot, so this is bound, bound. There are no free variables, no free agents, and what you're going to get when you write out the bottom equation, you will get y equals 0, and the top equation says x plus 2y equals 0, and well, y is already 0, so x is going to be 0 as well. So your null space on this one is just 0, 0. It's a subspace of R2. It's a trivial subspace, 2 being the number of columns. It's also the number of rows in this one because it was square. Let's do a few more of these problems. The reason I'm going to do problem 3 and 4 is just to emphasize you can find the null space of any kind of matrix. Look at this matrix here. It's a 1 by 3. The null space is gotten by going like this. Taking this, here's the equal sign, and putting a 0 there. I don't have to do anything to this matrix. It's already in row echelon form. It's in reduced row echelon form as well, but you just need row echelon form. And you just have to pick some variables like x, y, z. There's only one pivot right there, so X is bound. Y is free, Z is free. So Z is T, Y is S, and X plus 2Y plus 3Z equals 0. X plus 2S plus 3T equals 0. Did my camera turn off? No, it's still going. That's good to know. So X equals negative 2S minus 3T. Okay, so the null space on this one, it's not just a zero vector, it's an ordered triple, and it looks like this. This is negative 2S minus 3T, comma, S, comma, T. Now, because we have the S's and the T's, we put our brace there. We put a such that S and T are real numbers. And there's our answer. Now, some of you might wonder, why in problem 2 did I not put S and T are real numbers? Well, I still used set notation, except there were no parameters. There were no free variables. So this is acceptable. It's still set notation. Now we have infinitely many solutions. Okay, before we get to the last problem, this is our last null space, but we'll have one other thing that we want to look at. Find the null space of this matrix. Okay. The augmented matrix. We have 1, 2, 3, and then this one's 0, 0, 0. This one's a weird one. How many variables are there? There's just one variable, and I'll call it x. If you do row operations on this, you'll find that you can force that to be 0, the 2 to be 0, and you can force the 3 to be 0. So here's x. So what does that top equation say? That top equation says x equals 0. So what is the solution? It's 1 tuples, which is just regular numbers. Your null space then is 0. Now, I haven't been writing this on all the problems, but this equals, you don't have to do this, null space A. And that's really what we could have been writing on all the problems. So the null space will always exist for any size matrix because it's a homogeneous system. And a homogeneous system has at least one solution. Sometimes it just has one solution, and the other situation is when it has infinitely many solutions. Okay, the last thing I want to straighten up before we leave this section, which is 4.3 that we're doing, is on the test I asked you to find the inverse of a 2x2 matrix. I also asked you to find the inverse of a 3x3 matrix, which has to be done a longer method. But this one, there is a shortcut. So I encourage you, especially when we keep doing this and it spills into differential equations, you will want to know this shortcut for the inverse. So this is matrix A. The inverse is 1 over the determinant. The determinant is -3 minus a -8. So that looks like the determinant is going to be 5. Okay, because -3 minus 8. So make sure you know this shortcut, because look how fast it is. If I have to do the Gauss-Jordan technique on this, there's room for error. Switch your DNA. Negate your B and C. And then we write it as one matrix here. So we have -3/5, -4/5, 2/5, and 1/5. So if you were not doing the shortcut will save you much time. Shortcut only works on 2x2 matrices, but you know, I was seeing a lot of people in the test not doing that on the 2x2 matrix. So this completes section 4.3. You guys have a good day, and I'll see you in the next video.